Okay, welcome to the stream today. We're looking at part 2 of our Python PCI driver development, API, whatever you want to call it. So introduction, we have developed a PCI device. Let's go look at the thing. We have a PCI device that has the address space, and we're slowly adding features for like the ICAP, and for being able to read and write to the memory. And we played around that. So look at the previous, if you want to watch the previous video, we'll explain more of that. And in the previous video, we got the ICAP, we added a desync and a warm boot star, which is important for booting from Flash with PCIe devices. And we've already gone through that. So today, second section, this should hopefully go fairly fast, and then we can start the third segment today as well. The second segment, we're focusing on XADC. Those two features should be easy to do. And then the second part of today, we're going to look at being QSPI. I already have the commands for this kind of flushed out. We just need to put it into my new format with the new Python structure. So let's go ahead and get started with the XADC. So let's go ahead and move that screen. So first thing first, we have a ICAP. So let's just do XADC.py. Refresh that, pull it up, and all we're going to need to do, I don't think we need to import anything. So I think that should be the only thing we really need to worry about. And then we'll need to get some registers for it. The other view. See, and so we have basically two register values. We want registers, and if we go here, so the reset register is 00. So let's use the syntax that we had on our other one. So reg reset equals 00. Then we have reg temp. Reg temp is going to be 200. And then we need a mask value, which is going to be our reset value. So we have masks. So we're going to have reg reset mask. Oh, why do I have two pluses there? It should only be one. Process cleans. Do a quick clean. Okay. What else? So I think that should be here. And we'll bring in the equation, but this should be a fairly straightforward thing. Also the ICAP, we should probably go ahead and remove those features. But yeah, I think that should be fine, even if in the middle of doing something. So yeah, let's get the show on the road. Device address, base address, that all looks good. I think, yeah. And for now, we'll just print self.read temp. So let's go fill in those instructions. So def reset self. I think I just need to do something like this. Very simple. We're going to do the reset register. And we're just going to do. I'm happy that way. And seem to have messed that up. So that's all we're doing for the reset, and then for the temp, read temp. we're just going to do this. We're going to do a word read, and we're going to get register temp value, but we need self. And then we're just going to go ahead and do that. And then we're just going to have to do these different things. So we're going to have, call this raw temp with this. And then we need to get rid of the bottom 4 bits of raw temp. Yep, rid of those 4. And then we just got to do this map. Copy this over. And read temp there. Okay, and we're just going to put raw temp right there. And we should go and we should return temp, right? So now in our PCI script where we have ICAP, we're just going to move this to self.xadc equals XADC, and we're just going to do the same thing here. Instead of ICAP, we're going to do XADC register, and from here I do my macros. Now we just want to see. Okay, it looks like they all went through. So, seems fairly straightforward. Let's go to main. I want to get rid of that. We're printing out things I don't care about at the moment. Okay, so I think we went ahead and already finished the XADC portion of this. That seems fairly good. Those are all temperatures I would expect. This one's really hot. That's all I gotta say. These guys. So the first 4 are on one board together. We got one really hot one, and then the second board that has 4 must have better just passive air because they're doing much better. Yeah. Different temperatures for all of them. So let's go back here and start with our fun QSPI. We're just going to call it QSPI. Fine. We're going to open Notepad++. Go to other view. And then we're going to go up. We want to get SPI check. Pretty sure this is the one. Okay. How do we go about reading the ID on a SPI check? Okay. So let's go through here. QSPI. So we don't have registers. Well, we do have registers. We have registers, and then we have flash commands. So let's figure out what registers we have. So that's the chip enable register. status. How about we just pull up this documentation for the quad QSPI and go about adding these register values. Easier. Okay, so here's our address space. So, cool. Register reset is going to be 40 hex. What else we got? We got by control, so we're going to call it CR. Control register is 60. Status register 64. So data to write, that'd be 68. Data reading, VRR is going to be, let's see, reg slave. So this is kind of our ship enable for the flashes. It's slave select register. It took me a while to understand what it actually means, but it's just the chip enable signal that you usually see on a flash device. And when you look at our, let's see, I guess we could try to pull up the flash documentation. Let's see. This device. So, yeah, right here. Oh. Flash. So the chip select. Okay, cool. Yeah. We go down probably 3/4 of the way. Okay, so this chip select signal. That is the SSR register. Kind of directly relates to that. SSR. So we want the data transmit occupancy register. That sounds good. 74. No. 74, 78. This is going to be the data receive occupancy. And we are not doing interrupts, so we will not worry about that. Doing interrupts in FIFO, that sounds hard. Especially with Linux operating system. It's possible. Don't get me wrong, it's possible. An adventure for another day. Okay. Now, it's another A register. So sure, keep that there. It seems like a good stock. Okay. We'll go through the values as we need to go through here. Move that to other view. Okay, so we have our registers. Oh, and we have flash commands, so we'll do that. Flash command. Yeah, just copy that straight there. And from there, we'll see how it goes. So initializing our class. Yeah, let's just go ahead and do that. Okay, cool. And we'll start there. Let's define the reset. Define reset. Read ID, device info read, wait for busy, write enable. think the reset. So here's where I'm doing the reset. I'm just writing 40 here, and I don't think we want that. We want to do 186. So back to our other guy here. I start exactly with that same command, apparently, because the registers are thing. But we're going to so here, this is what we normally want to operate it at. So 186 for the command register. Well, the chip enable. We're going to do reg SSR chip enable I, and we're going to set that our active. We want to activate the chip enable, and this is basically going to be that. We just do. You want to do high? Do you want to do low? I don't want to do that. I want to do like active and deactive and idle. Maybe we'll just do that. Or do like an on. On, yeah, we'll do that. Okay, we'll do that better. I'm gonna do off, chip enable off. And we're just gonna do that. Like the best way about going about this. So I want to make sure our chip enable is off. Then the other thing, we want to get our command register. So let's look at what 861 means. So it's gonna be in here. Our control register, 861. So 6 is going to be 1 and 2. So let's look at 1 and 2. System enabled. We definitely want that. Yeah. So definitely want a 6 there. And then the 8. That's the inhibitor. That's what we want. And then the 8 is going to be pit 7. Right? What's this one? Because that's for the bit, right? That's going to be 4, 8 is going to be manual slave assertion enable. So I guess we could try it. And basically we're going to create 2 masks. It's going to be off and on. Off is going to be the 186, and on is going to be just 86. It's this last bit that's the inhibit bit. If this is down, that means it's going to be flowing transactions until the FIFOs are done. I'm not sure about that. We could play around with that, see if it still reads and writes. But we got to get a read working before we can verify that. So, do control register. We're going to do control register off. Okay. And that is going to be our reset. Now, next we want to do is a read ID code. But the read ID code, we're going to, let me see something real quick. Does he have a read? Does he have like an ID code? I don't know. Or registers, it's register 9. Does he have a register? No, he's not even doing it. So, we want to do the status clear. I mean, we're not even reading the status, so let's go ahead and just do this. This is the other status here. Is there any status bit that we want to care about? If I remember correctly, the status register here didn't do much information. Oh no, we have empty, full. So let's go ahead and add those. Right here. Reg, status register, RX, empty. Bit, bit 1. Probably like extend these fully so it makes more sense. It's going to be RX full. It's going to be bit 2, bit 3, bit 4, and 8. And this is going to be TX empty and TX full. Yeah, that's the one I think we really care about in this situation. Back here. So 70 is we're turning this off, and we're going to assume it's off in the first place. So let's not worry too much about that. So let's do def read ID. Let me put that self there. And yeah, that memory set again. Oh, we want to write bytes this time. We want to do a byte write. And to do that, I was curious. Turning to 8, self size. What do we call it? Here we go, byte array. Nope, a B array. And a byte read, byte write, and this may be hard to test. We'll keep that for now. I don't think it's super critical. We probably could do it either way. But yeah, let's go back to spy check. I think I needed 4 bits of addressing. So the device is off, so all we really need to do is write that FIFO. So we're going to do the data to transmit FIFO. We're going to do a command read. Now, all we're going to do is fill in zeros for the address. 1, 3, 2 more. And then we're going to turn chip enable on. Chip enable on. And then we're going to turn the transmit on. So transmit. And we want to read status, verify that, we're going to do, be right for for that portion. Now we want to read the status. So we're going to do a print text mem dot read, and we want to read the status register. So status register. Okay. And after we read the status register, we're going to take these, go the opposite direction. Yes. And this is going to go off. This is going to go. Yeah. And then we want to occupancy register is this right here. We have occupancy registers for both of these. So let's read DTRO and do transmit FIFO. And okay. And then we want to read data coming in. And we want to 1, 2, 3, 4, 5, 6. Really 6 reads. Okay. That's good for now. I think so. And we need to actually now do a self read ID. Okay. We're gonna go to the devices. Go ahead and comment out those two. Change up the order of these later. So this is going to be, we're calling it QSPI. QSPI. That address. Let's get it. Okay. Yeah. Let's see if it works. Otherwise, we're off to decoding. That password was wrong. We'll do this again. So. Register SSRCEN. Oh, you must have clobbered it somewhere. What's the first thing we're printing? Status register. 2 and a 5. Okay, time to do some debugging. Most of those bytes didn't work. Okay, that should be more information. Let's see if we're actually doing anything effective. One, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I mean, it says it has. Okay. We do a read ID. Okay, so let's print out, make sure we're doing the commands correctly. Yeah, forget about those later. Um, print. You want to print self dot offset. You want to do it here, right? Offset plus address, comma, x data. Just make sure doing what we expected it to do. Oh, we're getting the addresses we wanted. Maybe the buffers were just full last time. Okay, that works. Now, let us I'm curious if this will work the same way. That does not work. The reading works fine. So if we do self.array and I wanted to see 0x40 by 2 to what we want to say 7C. I just want to see if it looks the same way. This is going to be weird, but why not? Okay, cool. Excuse me. You read. Number 1. Yeah, it doesn't look like that byte array thing is working the way we expected. That was a guess. Not too worried about it. Yeah, it's okay if right. We're not doing any byte transactions, so I'm not too worried. If we wanted to, we could try do something fancier. So now I think I have to run it like twice. Okay, cool. We have 17s and 18s, that's all we need. So we're gonna do this. We need these reads. There we go. Oop. Oop. Doesn't work that way. There we go. Someone still printing arrays? You outlawed that practice. Did something happen? Or are we just not? So it's happy there. Maybe the status register didn't read it time. Yeah, read's important, I think. Slow it down. So there's read right here. So we're gonna do a little poll here. Need to do a little polling. Get this to work properly. So you see this 1 bit. So now I do it after here as well. There's a bit we're looking for during polling. So we basically want a 4. 4 says the TX FIFO is empty and the RX FIFO is not empty. So we're going to do a poll here. So we're going to do, we put a, should probably put a counter on it, but we are not those type of people. Let's just do this. We're just going to take a memory to this, and we're going to mask it with the TX empty mask. And we're going to say, as long as this does not equal the mask. And that should be good, right? Find out. Invalid syntax. We'll see, we'll put a plus there. Okay. Invalid syntax. Want me to pass. Times. Out. Self. Self. Okay, cool. Now, let me get better at these commands. And we can get rid of those. 1, 2, 3, 4, 5. Yep. That should get us what we want. 17, 18, 17. Beautiful. That is the ID. So we're going to do self.flash ID with that. And return value equals. Okay, that's good. So now let's go read the extended address space. Device info read. Device info read. So we want to wait for Flash not busy. Should be doing that, should we? That's really only critical when we're doing kind of an erase. But we should get that function up and running. That is clear. Not sure what's so important about clearing the status. Do you ever read the status? This is the only time I'm reading the status. Right here. We have a status register read, status register clear. The clear is about clearing out errors, which may be important. Okay, let's go look up at, what command is this, the 30? Let's go look up 30H in this document. I want to know exactly what it's doing. Okay. So this should only be executed before an erase or before a program. Do we need to clear the status? In case there are any previous flags. I mean, we could look. Let's look at the program fail flag. Okay. Well, maybe we can just find SR1. I assume I want to go backwards here. Status register. Okay, cool. Error occurred. Is there any here are two uses for this? Nope. If I back up here. Okay, so to be able to do so I think that's when dealing with the flash, right? So read. So we need to clear status bit, then make sure, then wait for it not to be clear on those three flash actions. But for this one, I don't think we need to do that. So let's go ahead and tackle the device info read. Could be fairly interesting. We're only looking for one. Okay. Or address read. Okay. Let's start it off then. So basically we're going to do this. But instead of that command, we are going to do call this command read device ID, I guess. And This one does not need an address. Need the right one there. So, but we want to do for I in range 81. How large this is. We're going to write that. And then we're going to do the whole initialize that going. And then for I in range 21 again, or 81, we're going to print out the hex values. Print I, comma, hex. And that should be it. Self.device. And then we'll save it to itself, and then we can reference it later. Make a fancy array. Like pass there. Invalid syntax. Turn. Doesn't like ending on a. Oh. That's all. Gotta get our parentheses to match up better, you know. Okay, cool. This is printing how we want. How is it? I think it's hex 21. So let me get this in hex, please. It's not like a little easier. I have to go hunt down this array. I think it's 21. Or was it 21 or 22? And if you want to, it just said greater than 0, right? So what do you want to say? 80. That there. 21 ends up on the 8. So yep. Okay, let's go find the documentation where we actually care about all these crazy values. For a big register map. Where is it? Look at the page from previously. Yeah, here's where we want it. Right there, 21. Because it should be yeah. So what do we have? So 19 right there. So we have a 2 and 19. So we need to do one more. Read. We should go to 50. How far are we going? for F. So if I were to say anything, you want 3 more here. That's 50. Need that there to make it line up. Go through. Maybe it didn't. Let's try again. Oh, maybe because we're reading extras. So let's go ahead and just read 55 and like layer up the buffer. Run it twice. Right up nicely. Two, 19, and then it's what? It's gonna be 21. So it's gonna be register 21. We're gonna care about in that situation. And quick question, calculator. And what number should we rerun ending on? 50. 50 should be ending on the 1. Okay. So let's print out. I want to print hex mem.read self.reg e arrow. Curious to how much things we have. Have to read. So it thinks we have 52. Read 2, we read the 50. Okay, so that's good. So we can get that. We got 52 after this. So you're saying I could lighten up that. Definitely need to read one more. We definitely need to read 51. And 50 there. Yep. It's total range. Now they're not going to line up because we read, so we're going to read 52. Looks good. Now we're going to go back here. We're going to read 51. And we're going to make a return value is going to equal return array. Return value dot append, and then we're going to return value. Okay, so the self.flash info equals that. We want to just print. I'm printing out hex for those. So self.flash ID info, and we're going to do what? 0x21. Yeah, let's see how that turns out, right? Do you think it is? Oh, the important part of returning the return value. Okay, and then we can go back to these wonderful hex. Okay, so 8s and 18s go, and then we have 9s and 17s, 8 and 18s, and 9 and 17s. This is important when we do flash erasing. Okay. Read ID, device info read. These are all kind of based upon write enable, program write. We're going to do a random read. Okay, so we can do this simple way and shorten it to 128, but I want to get it up to 256. So we're going to just do the commands and then fill it up and read it out. Okay, so we're going to try that about zip select. So next we're going to do a read. And since we're not as we're beginning this read, we're not going to worry about the clear status just yet. So we want to random read. So let's go look at the random read real quick and see how many bytes we can actually read of a random read. 13H. The read. Oh. That. So we can read as much as we want. It makes life so much easier. We just gotta build a quick system for that. Fast read. The 133. 50. 133. I don't think we have dual output. We could try to do a read. We look at the design much. Where's my sorry? How many bits wide is this sucker? Here. We have mode quad. External SPI clock. Our external SPI clock is running how fast? which is 100 megahertz. So I think we're running our SPI clock just twice as fast as more a bit. That's an interesting question. We're running our SPI clock that fast. How are we reading the SPI so well? See. What happens if we have quad? You know, quad. I want to read this thing like as fast as possible. How do we get this status register? Dual and quad mode. That's cool. Keep going up. Okay, so I'm trying to figure out the fastest way we can read this. Okay, let's see if we can figure out how to do a quad read. Um, interesting. It's gonna be interesting to see if the read works. So, an issue we have, my previous clock may have been running at a slower speed. We may have to resort to the fast read. So what we're going to do is we're going to try to implement the slow read and see if we get anything out. But we're just going to do a standard slow read. So we're going to do self address. You know about that. Basically, we're just going to do a read command. This command may not work because we changed the clock frequency, apparently. Yeah, I mean, we could just do basically this, right? But instead of, we're just going to do a read command. and the address is already in there. So let us just print text around print south dot random read for 0, right? See what happens. I'm curious. That looks right. Okay, I mean, let's not worry about returning right now. Let's just do print text. Oh, we're gonna see this. So that looks like it's from something else. That's okay. That looks good. That looks good. Looks good. So let's try. What was the fast read? Fast read is do a 0C. 0C. See what happens. I'm curious. And yeah, there's an extra byte. Seems to be all good. We'll do verify and so do the reads and the writes later. Now I want to see if we do a dual output. So do a 3C. This actually worked. But how quickly does that compare? Remember we had that print hex. Do a read. DR. Oh, right. Curious. Now let's save these data. So we have 113 is the first read. Uh, 51. And let's hold an Excel, right? Okay, so we have an Excel here. We're just going to do that. And let's do 1, 0, and 0, enter 1, and then vote. Oh, we done. I have another. Okay. So we wanted to try a 0C, supposedly the fast write, a fast read. There's the dummy byte. I mean, that makes sense. Right here. So we have the additional dummy byte. And everything else looks the exact same. I like grabbed way more than I wanted to. Okay. Now we want to try the 3C. Is the full data rate. I don't know how the system interprets this. Still says 51. And it looks the same. I don't see any issues. Now, is there any more crazy stuff we should try? I mean, the average read is working. I'm not really concerned. 6CH is our last one, right? I wonder if the flash. I'm hooked up, so it doesn't really matter what read you do. That one. Okay. Here, the 6CH. Anything interesting? Bunch more C's. Here's where the C's came from. It's just the LC. What do the LC stands for? Looking at this, I think we should be fine with the normal read. So we're going to 15. And not worrying about the other ones after a little experiment. Okay. What we're going to do is we're going to write the address, erase, pause, and then read things. So let's see if we can do that. It doesn't matter where we read from. So we need to break down the address. Okay, we're back. Figure out this QSPI. Remember, I should be focusing on other things. The QSPI is not too critical at this moment. So let's get the read to do 56 space. Well, we could just do get this going, and then I'll be happy. And I'll need to learn how to connect videos together. But yeah, so the address, let's do this whole byte array thing. I like this idea. And so we're going to do memwrite, and we're just going to right there. Okay. Clip on. So the off here. And then we need to read. While what we're going to do is read, right? We're going to do receive register, and we're just going to read that, boom. And then we're taking this guy, we're going to do 250, we're going to do FIFO is 256 volts. Oh, actually no, I know what we're going to do. What we're going to do, full flag. Long as the full flag. Then we're going to return this on. Turn it on. I'm going to read. And we'll need this again, the pause for the break. And turn it all off. And then we're going to do, this empty thing, we're going to do that. Okay. So we see how this goes. I'm curious. Nice and clean. Oh, beautiful. It starts right on top of it. Ah, great. So we got the read for now. So it's like a return array, and I assume we would just loop back over and over if we want to keep reading, but for now we're only going to support 256. And that's where we're going to end this segment. Okay. And here. So we're going to print hex read value, and we're going to do what? Which one should we do? Let's see what, like 40? Curious to what 40 gives us. 40. Okay. There we go. I want a better value to read. Can we say 36 to 40? Oh, apparently I was fast. Oh, it's a whole hex thing. Hex now. Hex expects a string. Why can't you be smart enough to just take my array and individual values? That looks good. We want BB. BB is going to be 35. 35. Like that. Make sure everything's going well. Okay, so I'm gonna add the short recording there and may try to add the 6 minutes to a previous recording. I don't know. Well, thanks. Maybe we'll jump on. And I think I'm gonna skip the rest of the QSPI read Flash writing, which is important. I gotta focus on other things to get some tests up and running.